1943, Supermarine Aviation Works, Southampton. The new Rolls-Royce Griffon engine had turned the legendary Spitfire into a wild beast. Nearly 2,000 horsepower of untamed power twisted the aircraft like a cork in water, forcing pilots to battle the controls just to keep it level. Every engineer in Britain knew the fix had to be simple, proven, and reliable. But Joseph Smith thought differently. Twin propellers spinning in opposite directions on one shaft. His colleagues mocked the idea, calling it foolish, too heavy, too complex, and too fragile for war. The Ministry of Aircraft Production dismissed it completely. But when the first modified Spitfire took off and reached 470 meters without a wobble, and pilots reported handling so smooth they could aim perfectly in combat, everyone wanted to know how a stupid idea became the Allies' deadliest secret. The autumn rain of 1943 drummed against the hangar roof at Supermarine Aviation Works. Each drop marked time Britain couldn't spare. Inside, under harsh industrial lights, mechanics worked frantically around what should have been the Royal Air Force's greatest weapon. The Spitfire Mark 21 promised everything the Allies needed: speed, firepower, and the same agility that had saved Britain during the Blitz. But something had gone terribly wrong. Squadron leader James McKinnon climbed out of the cockpit, drenched in sweat despite the cold October air. His hands shook as he pulled off his gloves, not from fear, but from sheer exhaustion after fighting 2,000 horsepower of barely contained chaos through the skies over Hampshire. The Griffon engine had made his beloved Spitfire feel more like a bucking bronco than a fighter plane. How bad? Asked Chief Engineer Malcolm Whitfield, already seeing the answer in McKinnon's face. At 350 MPH, she wants to roll left so hard I almost spun out, McKinnon said, his Scottish accent thick with frustration. That engine torque, it's like the propellers trying to rip the nose off above 400 mph. Forget it. No pilot could hold her steady in combat. The data confirmed it. The Griffon 65 engine produced 1,250 horsepower at sea level, almost double the Merlin's power. In theory, that should have made the aircraft exceed 470 km faster than any German fighter. But Newton's equal and opposite force twisted the frame so violently that pilots couldn't keep the plane straight at full speed. Whitfield ran his hand over the propeller hub, feeling a faint vibration that never stopped, even with the engine off. The problem was simple to explain, but nearly impossible to fix. Each revolution of the massive propeller created a force that tried to spin the aircraft the other way. At low speeds, pilots could fight it with rudder control, but at high speeds, the effect grew dangerously strong. The faster they flew, the more unstable the plane became, exactly the opposite of what they needed in war. The Germans faced the same issue, Whitfield said. Their Focke-Wulf 190 struggles with torque too, but they handle it through pilot training. McKinnon shook his head. You can't train around physics, Malcolm. This isn't about skill, it's about limits. At the speeds we need over Europe, this plane's unflyable. Everyone in the hangar knew what that meant. The ministry had poured millions into the Griffon and the redesigned airframe. Dozens of units were already scheduled for production. The Navy needed the Seafire variant for carrier combat in the Pacific. Failure wasn't just an engineering flaw. It threatened Allied air power at a crucial point in the war. 15 miles away, in a cluttered office at Rotol Air Screws Limited, Joseph Smith sat surrounded by drawings, slide rules, and half-empty teacups. For a week, he'd studied every flight test from the troubled Spitfire, searching for an answer no one else could see. The usual fixes, bigger rudders, engine mount tweaks, altered blade angles, all failed. Each one either added weight, weakened structure, or caused new vibration issues. At 42, Smith's reputation was mixed, brilliant but unpredictable. His designs for Rolls-Royce propellers often pushed manufacturing limits, earning respect and frustration in equal measure. His colleagues expected bold ideas, but nothing like the one he revealed that grey October afternoon. Instead of fighting the Griffon's torque, Smith proposed using it, a contra-rotating propeller system. Two propellers on the same shaft, spinning opposite ways, cancelling each other's torque and delivering unmatched thrust efficiency. It was daring, elegant, and unbelievably difficult to build. The system needed a complex gearbox to drive both propellers from one engine, perfectly balanced to avoid deadly vibration and strong enough to survive combat. Most of all, it had to be reliable in mass production. When Smith showed his plan to the team at Rotol, the response was instant and brutal. Senior engineer Robert Morrison called it a mechanical nightmare. Production manager Charles Henley worried about weight and maintenance. Test engineer David Clark doubted it could handle carrier landings. It's just too complicated, Morrison argued. You're talking about two full propeller systems working together in perfect sync. The gear ratios alone would need precision we can't manage in wartime. But Smith had done the math. The setup would add about 200 pounds, but by removing torque, the Spitfire could finally reach its full speed potential. More importantly, it might just save Britain's skies. Improved propeller efficiency would boost thrust by nearly 15%, more than making up for the extra weight. The Spitfire Mark 21 could finally become the 470mm interceptor the Royal Air Force desperately needed. As autumn faded into winter, the argument over Smith's foolish propeller design would decide not just the fate of Britain's most iconic fighter, but the balance of air power across Europe and the Pacific. The Ministry of Aircraft Production's boardroom in London felt more like a courtroom than a meeting when Smith arrived on November 15th, 1943. Around the polished table sat Britain's top aviation officials, their faces lined by 4 years of war. Air Marshal Sir Wilfrid Freeman led the session with the cold focus of a man who had seen too many failed aircraft programs. "Mr. Smith," he began, his clipped RAF tone firm, "we've reviewed your contra-rotating propeller proposal. Our technical teams are skeptical." He motioned to a pile of reports stacked high beside Smith's thin folder of drawings. "The consensus is that your system adds needless complexity at a time when we need simple, proven solutions." Smith expected resistance, but the formal atmosphere made his pulse quicken. These men decided the direction of British aviation. Their verdict would decide whether his sleepless nights and endless calculations had any purpose. "Sir," Smith began carefully, "the system's complexity is what makes it effective. We're not adding parts. We're solving the torque issue that's made the Griffon engine uncontrollable at combat speeds." Sir Roy Fedden, Director of Technical Development and one of Britain's leading engine designers, leaned forward. "Mr. Smith, your gearbox would be the most complicated ever mounted on a fighter. Dual shafts, planetary reduction gears, and perfect timing under combat stress. Maintenance alone could ground entire squadrons." Smith's data told another story, but he knew numbers alone wouldn't change minds. "The gearbox complexity is manageable with precision manufacturing. De Havilland already mass-produces variable pitch propellers. Our design uses a two-stage planetary gear train, 0.77.1 reduction for the front propeller and 0.62.1 for the rear. The differential speeds cancel torque while maximizing thrust." Group Captain Peter Thornton, representing operational needs, flipped through combat reports. "Even if it works mechanically, the Mark 21's already heavier than older models. Add 200 pounds of propeller gear, and we risk performance changes we don't yet understand." Smith produced his final calculations. "The extra weight is real, but the benefits outweigh it. We project a 15% thrust gain with zero torque reaction. The Spitfire will not only hit 470 MPH, but remain stable across its speed range. Tests show danger above 350 mph. Our system keeps us safe past 400. What he didn't mention were the alarming intelligence reports. Ultra intercepts revealed Germany developing faster Me-262 jets and improving the high-altitude Focke-Wulf TAR 152. The Allies needed every edge in speed and control to win air superiority before the invasion. Freeman studied his notes, weighing risk against necessity. "Your plan would require major production changes. How long for a prototype if approved?" 6 weeks for gearbox design and machining, 4 more for propeller balancing. Flight tests by early February, Smith replied, masking how difficult that would be. The contra-rotating setup demanded extraordinary precision, gear cuts to chronometer standards and propellers balanced within fractions of an ounce. Silence filled the room. 6 months had passed since the first failed Griffon test flights, and combat units were running out of patience. They needed aircraft to rival German fighters, especially at altitude where the Griffon should dominate. Finally, Air Commodore Ralph Sawley, veteran of the Battle of Britain, spoke. "Mr. Smith, your reputation precedes you. When you bring us something this unorthodox, it deserves serious thought. But tell me honestly, are you absolutely sure it will work? We can't afford another failure." Smith met his eyes. "Sir, I stake my career on it. The physics are sound, the engineering is within reach, and the results will be exactly what the RAF needs. The Spitfire Mark 21, with contra-rotating propellers, will be the fastest, most agile fighter in the world." The words hung heavy in the air. Freeman glanced at his peers. Smith's record spoke for itself. His designs were bold but effective. "Very well," Freeman said at last. "We'll approve 1 prototype, full flight testing and performance review. But know this, if it fails or delays production even a month, the fallout won't end with you." As Smith gathered his papers, the weight of that warning settled on him like lead. The coming months would decide whether his crazy invention transformed fighter aviation or became a lesson in arrogance. Either way, Britain's skies, and perhaps the war's outcome, now depended on gears and propellers spinning against every rule of aircraft design. The morning of February 23rd, 1944, broke grey and cold over Salisbury Plain. Winds lashed the test field at Boscombe Down, where inside Hangar 7, the modified Spitfire, Mark 21 waited, an alien machine among its conventional kin. The massive contra-rotating propeller assembly dominated the Spitfire's nose, giving it an almost predatory look. The twin propellers, each 11 feet across, created an optical illusion that seemed to defy the very rules of aviation engineering. Test pilot squadron leader Geoffrey Wellham approached the aircraft with the calm focus of a man who knew he was about to risk his life on an untested idea. At 24, Wellham had already survived 3 years of combat over Britain, France and Malta, logging nearly 800 hours in various Spitfire versions. His reputation for precision flying made him the ideal choice for this experimental mission, but nothing in his experience had prepared him for the mechanical complexity. Bolted to the front of Spitfire RK958, the contra-rotating propeller system was the product of 6 months of relentless engineering. By Smith's team at Rotol, the front propeller turned clockwise at 1,225 RPM, while the rear spun counterclockwise at 1,275 RPM. Between them sat a 193-pound gearbox, machined with clock-like precision. Every part was balanced to within half an ounce, yet the system still produced a faint vibration that pulsed through the airframe like a mechanical heartbeat. Chief Test Engineer Michael Lithgow oversaw the pre-flight checks with visible tension that spread through the hangar. "Gearbox temperatures normal during ground runs," he reported, clipboard in hand. "Oil pressure steady at 60 pounds per square inch. But Jeff, we're still seeing harmonic vibration around 1,800 RPM that we can't explain." Wellham ran his hand along the propeller hub, studying the intricate design that made a normal single propeller setup look primitive. "What's the test plan?" he asked. "Conservative," Lithgow replied. "Climb to 8,000 feet, level flight at different power levels, then slow increases up to 400 miles per hour, if control remains stable. We're watching for torque effects and any strange handling." Smith stood quietly near the port wing, his expression calm, but his stomach tight. This moment was the peak of his career, and it could also destroy it. Every equation had been checked, every part tested to its limit, yet aircraft design always carried an element of risk. At exactly 9:15, Wellham strapped into the cockpit. now filled with extra dials monitoring the new propeller system, engine oil temperature, gearbox pressure, forward and rear pitch angles. The Griffon engine started with its familiar deep growl, but the twin propellers transformed the sound into something entirely new, a layered harmony that seemed to echo through his bones. At 9:32, ground control cleared him for takeoff. He eased the throttle forward, and the Spitfire rolled down the runway with surprising smoothness. The usual left-turning pull was gone. The contra-rotating blades cancelled the torque perfectly. For the first time in months, a Mark 21 lifted off straight without pilot correction. Takeoff occurred at 85 mph, exactly predicted, but the climb felt sluggish. The plane needed more power than expected to gain altitude. The added weight of the propeller system clearly hurt performance more than Smith's numbers had shown. By 5,000 feet, Wellham was near full throttle just to maintain a 2,000 feet per minute climb, something that should have been easy at 3/4 power. "Boscombe Control, this is Test 27, he radioed. "Climb performance below expectation. Request to level at 6,000 for handling check. Test 27, cleared to level flight. Report handling," came the reply. Reducing power, Wellham found the aircraft surprisingly stable. Despite weak climb performance, the Spitfire felt smooth and balanced. The absence of torque had changed everything. Handling was crisp, the airframe steady, almost serene. At 300 mph, the plane that once tried to roll uncontrollably now flew with exact precision. He tested gentle turns, steep banks, and rapid rolls. The aircraft responded gracefully, like the original Battle of Britain Spitfires. For a moment it felt as though the legend had been reborn. Then he pushed the throttle toward full power, and the dream shattered. Instead of accelerating smoothly, the aircraft began to shake violently. At 370 mph, the vibrations became terrifying. Instruments blurred. The frame rattled like it was about to tear apart. The twin propellers, meant to work in perfect sync, were instead clashing in destructive harmony. Boscombe Control, Test 27, severe vibration above 370, reducing power, returning to base. Emergency landing. On descent, another issue appeared. With power at idle, the Spitfire dropped faster than expected, forcing Wellham to keep adjusting throttle to stay on the glide path. The new system's weight and aerodynamics had reshaped the entire flight envelope in ways no one had foreseen. He landed safely after 43 minutes, but his grim expression told the story. Smith's invention had worked. Torque was gone, but it had created new dangers. Ground crews rushed in to inspect the aircraft for damage as Smith approached quietly, his face pale. The test pilot's report would decide the fate of the project, whether it continued or joined the long list of failed wartime experiments. 2 hours later, an emergency meeting gathered in Hangar 7. Smith stood surrounded by engineers, pilots, and officials, their faces filled with frustration. Behind them, the Spitfire sat motionless, its twin propellers still and menacing, a silent reminder of how thin the line was between genius and disaster. Air Commodore Sawley had driven down from London for the debrief, turning what should have been a technical discussion into something closer to an inquest, into something that felt more like a court-martial than a technical debrief. "Squadron Leader Wellham," began Air Commodore Sawley, his tone carrying the full weight of command. "Please give us your complete evaluation of the aircraft's performance during today's flight." Wellham stood at attention, his flight suit still damp with sweat from wrestling an aircraft that had nearly shaken itself apart. "Sir," he began evenly, "the contra-rotating propellers completely removed the torque effect during takeoff and low-speed flight. The aircraft tracked perfectly straight without rudder input, and handling below 300 mph tonnage was exceptional, perhaps the best I've seen in any Spitfire." A ripple of surprise moved through the gathered engineers, despite the alarming end of the flight. Wellham's early observations confirmed that Smith's invention had solved the Griffon engine's most dangerous flaw. But his tone darkened as he continued. Above 370 mesoterm, the aircraft developed severe vibrations that made higher speeds impossible. The shaking was violent enough that I feared structural failure. Climb performance was also poor. We needed nearly full throttle to achieve rates that should have been possible at 75% power. Smith felt the blow like a physical weight. 6 months of effort, precision machining, and reputation had led to an aircraft that excelled at low speeds but failed at the exact point it needed to shine. He had fixed one deadly problem only to uncover another. Chief Engineer Lithgow flipped through data sheets, looking for clues. "Our ground tests showed mild harmonics at certain RPMs," he said, "but nothing close to what Squadron Leader Wellham experienced. It seems aerodynamic forces at high speed triggered resonances we didn't anticipate." Sir Roy Fedden leaned forward, his voice sharp. "Mr. Smith, your calculations must have included aerodynamic effects. How do you explain this difference between prediction and reality?" Smith had spent hours running through that same question. "Sir," he replied, "our data came from static and wind tunnel tests. In flight, 2 contra-rotating propellers create complex airflow patterns we can't fully model. The tip vortices seem to interfere with each other, producing destructive resonance we didn't see on the ground." It was a scientifically honest answer, but it brought little comfort to officials who had invested heavily in the project. Sawley's expression hardened. He was already calculating the political fallout. "The real question," he said flatly, "is whether these problems can be fixed quickly, or whether we should abandon this design entirely." Smith's career hung in the balance, but the engineer in him refused to yield. "Sir, the vibrations can be solved. We can modify the blade geometry and adjust gearbox. Timing. The core concept is sound. The goal now is to eliminate aerodynamic interference." To everyone's surprise, Wellham spoke up in support. "With respect, sir, the aircraft's control below 370 MPH was extraordinary. If Mr. Smith can fix the high-speed resonance, we'll have a fighter that combines the Griffon's power with better handling than anything flying today." The room fell silent as everyone weighed risk against urgency. Intelligence reports warned that Germany's new fighters were progressing fast, and the upcoming invasion of Europe would demand total air superiority. Smith seized the moment. "Our analysis shows the issue lies in the propeller blade angles and speed ratio. If we alter the gear ratios to change the relative RPMs, we can shift the vibration frequencies away from the resonance point. Adjusting blade twist will also reduce tip vortex interference." Lithgow looked up from his notes, cautiously hopeful. "Those modifications would take about 3 weeks of machining and another week to rebalance everything. We could have her flight ready by mid-March." Sawley checked his watch, calculating timelines and production pressures. The ministry could not afford endless experiments. "Mr. Smith," he said finally, "you have one last chance. If the next flight doesn't show clear improvement, the contra-rotating program ends permanently. We'll return to conventional torque reduction methods." When the meeting ended, Smith stayed behind, staring at the silent Spitfire. The machine looked ordinary again, its revolutionary propeller system now just another piece of metal awaiting revision. Yet in his mind, he could already see the changes that might save it. The next 3 weeks would decide everything. Either his stupid idea would transform air combat or end his career for good. The fate of Britain's most famous fighter now depended on nothing more than gear ratios, blade angles, and the invisible physics of spinning air. As night settled over the airfield, Smith began sketching modifications in the dim light of Hangar 7, lines that would either redeem him or ruin him forever. The morning of March 18, 1944, dawned clear and calm over Boscombe Down. Conditions: seemed almost too perfect for what all present knew was the final test of Smith's controversial design. 3 weeks of round-the-clock work had reshaped the contra-rotating assembly into a subtly new form. The changes were invisible to anyone but Smith. Tiny adjustments in blade geometry and gearbox ratios painstakingly recalculated to tame the deadly vibrations that had nearly destroyed the aircraft on its first flight. The key lay in altering the propeller speeds from the original 1,125 and 1,475 RPM relationship to a new setup of 1,700 and 1,500 revolutions per minute. The closer speed difference shifted the critical vibration frequencies away from normal operating ranges while preserving the torque-cancelling benefit that made the system so valuable. Smith's team also redesigned the propeller blade twist, softening the sharp angle changes near the tips that had caused violent air vortices. Each blade now featured a smoother transition from root to tip, reducing aerodynamic interference and preventing destructive resonance at high speeds. Achieving this required hand-finishing each blade to thousandths of an inch, 2 weeks of painstaking craftsmanship. Squadron leader Wellham approached the modified Spitfire with cautious hope, haunted by memories of the violent shaking from his previous flight. From afar, the aircraft looked unchanged, but up close, the subtle differences hinted at transformation. The new blades caught the morning light differently, their refined geometry casting sharper, more purposeful shadows. Ground tests are perfect, reported Chief Engineer Lithgow, tension tightening his voice. Stable power through the full range, no harmonics. Oil temperature steady, and the new gear ratios eliminated the resonance bands we found earlier. Air Commodore Sawley had returned from London to witness the test personally, bringing with him an unspoken sense of finality. The Ministry of Aircraft Production could not fund experiments forever, not with D-Day looming. This flight would decide not only the fate of Smith's invention, but the future of British fighter design. At 10:15 a.m., Wellham started the Griffon engine and instantly sensed the difference. The sound was still complex, but now smoother, less harsh. Engine readings were normal as he began taxiing, and even on the ground, the vibration that had plagued the first prototype was gone. Takeoff at 10:28 revealed the biggest improvement. Where before the Spitfire had needed full throttle to climb, it now rose effortlessly at 2,000 feet per minute, using only 80% power. The refined propeller geometry had unlocked the Griffin's full potential, turning brute force into elegant performance. Boscombe Control, Test 27 climbing through 8,000 feet, Wellham radioed, his voice edged with excitement. Climb rate significantly improved, handling excellent, request clearance for speed tests. Test 27, you're cleared, came the reply. Use caution near prior problem zones. Leveling at 10,000 feet, Wellham began testing the same range that had nearly ended his career 3 weeks earlier. At 300 MEP, smooth. At 350, still perfect. As the airspeed reached 370 MEP, he braced for the shudder that once threatened to tear the aircraft apart. It never came. The Spitfire surged ahead, stable and strong. At 400 mph, it felt steadier than most fighters at half the speed. Boscombe Control, Test 27, now at 410 mph, Wellham reported, his tone shifting from caution to exhilaration. Aircraft completely stable, handling exceptional, performances remarkable. From the tower, Smith watched through binoculars as his Spitfire carved clean arcs through the bright Hampshire sky. The twin propellers converted the Griffin's brutal power into precision and grace, vindicating months of risk and ridicule. This was proof that unconventional thinking could triumph over conventional limits. For 25 more minutes, Wellham pushed the aircraft through every maneuver. High-speed dives topped 450 mph without instability. Tight turns held together beautifully, combining the classic Spitfire agility with raw Griffon power. Landing at 11:32, Wellham taxied back, his grin visible even before he climbed out. "Gentlemen," he said, removing his helmet and turning to Smith, "what you've built isn't just a better Spitfire. It's the finest fighter I've ever flown. Speed, handling, control, it's beyond anything in service anywhere." Air Commodore Sawley stepped forward, his once stern face softened by reluctant admiration. "Mr. Smith," he said formally, "congratulations. Your contra-rotating system has exceeded every performance prediction. The next question is, how soon can we begin production?" As the engineers and officers gathered around the aircraft, Smith stood quietly beside his creation, pride mixing with realism. The real challenge was just beginning, turning one brilliant prototype into an operational fleet. That meant manufacturing precision, pilot retraining, and supply chains stretched to their limits. But for now, standing beside the Spitfire that had proved him right, Joseph Smith allowed himself one rare moment of triumph. Against every doubt and every failure, his stupid idea had worked, and in doing so had given Britain a fighter so fast, so stable, and so advanced, it might very well change the course of the war.